Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed some applications of the linear algebra. So, today we are going further for that one. So, let us start with this. So, today I want to give you one definition of the basis. So, as we already know that if suppose a linearly independent spanning set for a vector space that V is called a basis of the vector space V. So, it is the linearly independent spanning set. It should be linear independent and it should be a spanning set also. So, that definition we already know. So, now based on this one I want to write characterization of a basis. So, what are the characteristics of a basis? Now, suppose let U be a subspace of a vector space, say Rm, and let I take a set beta that contains the elements B1, B2 up to Bm, and they are belongs to the subspace U. Then the following statements are equivalents. So, in this case we are taking the U as a subspace and we are taking the vector space Rm, the m dimensional vector space, and let I take the set beta which contain the vectors B1, B2 up Bn. So, this is the n number of vectors and that are contained in the given subspace U. Then the following statements are equivalent. So, the first one is that beta is a basis of U. Second one, beta is a minimal spanning set for U, and the third one is that beta is a maximal linearly independent subset of U. So, all these three statements are equivalent. So, suppose I just take this one. So, now this can be discussed. Now, we have a beta. So, beta is containing the elements B1, B2, Bn. Okay, so that we are taking n number of vectors, and I know that the V is the dimension of V that is equal to m in this case. Now, if I say that the beta is a basis of V, implies that the set beta is linearly independent because these are the bases, and U is spanned by beta, or I can say that it is spanned by the vectors B1, B2 up to Bn. So, then it becomes the basis. Now, the next thing says that beta is a minimal spanning set for U. It means if I say that beta is a minimal spanning set for U, it means that there cannot be a smaller set which contains the vectors less than n can be a spanning set for U, which implies that there does not exist any set having vectors less than n which are the basis for U. Less than n means suppose n is 5, so I cannot have the set which is less than 5 and which is also the basis for the vector U. So, this is the statement about the minimal spanning set. So, this can be seen that suppose let us go by contradiction and we can prove this one that. So, let us go by contradiction. So, let beta is not a minimal spanning set for U, which implies there exists another set, say alpha, such that, so if it is not a minimal spanning set, it means there is another set alpha such that alpha such that the number of vectors in alpha are Li and also spans U. And of course, if it is a minimal spanning set, alpha is a minimal spanning set, then also that this number of vectors will be less than, or maybe I should take it can be less than n, because if it is not the minimal, it means alpha is the minimal, and if alpha is the minimal, then it definitely it will contain the vector less than n numbers, and which are also linearly independent and spans U. Now, alpha contains n number of linearly independent vectors. So, from here what you are getting that beta is also one of the bases for U, and alpha is also one of the bases for U, and which having the less than number of which has the vectors number of vector less than n. So, which implies that, so this things is which is not possible, because if I say, so this can be seen that if I say that the dimension of U is n, then its basis definitely should contain the n number of elements. But here if it is I take alpha as a minimal spanning set less than beta, then it contains the vector less than n, so which is not possible. So, from here we can say that this is the minimal spanning set. So, this way we can prove these things. So, which implies that beta is a minimal spanning set for u. Now, the same way we can discuss the third one. So, third one says that beta is a maximal linearly independent subset of u. So, it is the maximal linearly independent subset. We cannot have a subset of u which contain the linearly independent vector having more numbers than this set beta. So, let us prove this one. So, let us do this one. So, we go by the contradiction. Let beta is not a maximal linearly independent subset of u. So, it is not the maximal linearly independent set. It means that suppose I have a set S which contain the elements, maybe I can take the elements as V1, V2 up to Vn, Vn plus 1 or maybe Vk. So, it contains the k number of vectors and S is linearly independent. It means the vectors are linearly independent. So, it means that I am considering that beta is not the maximal linearly independent subset of u. So, if it is not the maximal linearly independent of u, I take the another set S which contain the linearly independent vector which are in number k, that is more than the n. So, here I am taking that the k is more than n. Now, we already know. So, if it is a maximal, which implies, so if it is not the maximal, this is the maximal. Now, from here I can say that the set S is linearly independent and it also spans u. So, which implies that S is a basis. Now, if it is a basis for u, but we already know that the dimension of u, but we know that basis of u cannot have more elements, more vectors than the dimension of u, because if u is a n dimensional, then its basis cannot have a more vectors n in numbers. So, which implies that but k is greater than n. So, from here I can say that since k is greater than n, which implies that the set S cannot be linearly independent, because it is a, if it is a basis containing n elements, we know that the more elements than n will be linearly dependent. So, which is a contradiction. So, which implies that the given set is the maximal set. So, that shows that beta is the maximal linearly independent subset of the vector subspace U. Now, after that we also know one of the another definition. We know that the dimension of a vector space V is number of vectors in its basis. So, that we already know. So, based on this one, I want to discuss one theorem. Let U be a subspace of a vector space V. So, we are talking about finite dimensions vector space. So, let U be the subspace of the vector space V, then dimension of U will be always less than dimension of V, because U is a subspace of V, and if dimension of U is equal to dimension of V, so that implies that U will be equal to V, this one. So, this is the another important theorem. Now, this one we can see very clearly, since U is a subspace of V. So, I can say that U is a proper subset of V, that is U is proper subset of V. I am considering that it is not equal to V, which implies that there exist some elements V such that V belongs to capital V, belongs to the vector space and does not belongs to the given subspace U. It means dimension of U has to be less than dimension of V, because I get a one vector which is not belonging to the given subspace. It means that the basis of U cannot span the entire V, because V is a one vector I found which is containing in the given subspace U and which is not in the V. So, that implies the dimension of U is equal less than equal to dimension of V. Also, if dimension of U is equal to dimension of V, which implies that number of vectors in basis of U is equal to number of vectors in basis of V. And we know that if V is a n dimensional vector space, then all the bases will contain n number of vectors. So, which implies that this is possible only when U is equal to V. So, from here I can say that if the dimensions are same, then the set U and V will be same. So, this is another important terminology. Now, there is another theorem we want to discuss, that is called extension theorem. So, in the extension theorem, basically what we are going, let the set, I take a set which contain elements V1, V2 up to Vk. So, let the set which contains k elements be a linearly independent subset of an n-dimensional vector space V, then we can find vectors, that is Vk plus 1, Vk plus 2, V up to n in V, such that the set, now I take the set V1, V2 up to Vk, Vk plus 1, Vk plus 2 up to Vn is a basis for vector space V. It means if I have a vector space, n-dimensional vector space, and in that vector space if I get a set of vectors, k number of vectors, which definitely k is less than n, then we can extend these vectors, because these are linearly independent. So, I can extend these vectors to the n numbers such that it become the basis for the vector space V. So, in that case it will be a linearly independent as well as it will span the whole V. So, this is the extension theorem. So, this theorem will use in future for the extension of the basis. Now, I want to discuss a very important theorem, that if U and W are two subspaces of a vector space V, that is finite dimensional, then dimension of U plus W is equal to dimension of U plus dimension of W minus dimension of U intersection W. So, in this way we can find out directly the dimension of U plus W, because we already know that U intersection W is also a subspace of V, that we already know, and we also know that U plus W is also a subspace of V. So, that two things we already know. So, this condition will be held. So, let us do the proof for this one. So, let I take that, let first I assume that the let dimension of U, I just take M, dimension of W I will take P, and dimension of U intersection W I will assume R, and dimension of V I will assume that is N. Now, of course, M, P, R definitely it will be less than equal to N, because it is a subspace. So, definitely it will be dimension will be less than equal to N. Now, I will take that let I will take a set V1, V2 up to VR be a basis for the subspace U intersection W, which implies that U intersection W is a spanned by this one, and these are linearly independent. Now, so I just call this set, maybe I will call S. Now we know that S belongs to U and S also belongs to W, because these vectors will definitely will lie in the U also and W also, because they are belonging to the intersection. Now from here, so the set S, so this is the set which contain the R number of vectors, can be extended to the basis of U, because this set also belongs to U, but I can extend with the help of extension theorem, I can make the basis of U. So let I take the set V1, V2 up to VR, VR plus 1, VR plus 2, Vm. So I will take, or I should, instead of V, I will take them as a U. So let us take U. And UM. So this is be a basis for U. Now, since S also belongs to W, so which implies using extension theorem. So using extension theorem, we can extend the set S to a basis of vector space subspace W. So which implies I can have a vector, the set of vector V1, V2 up to VR, and then I can write W R plus 1, W R plus 2 up to W R, so it goes up to P, so it is P. So now is a basis for W. Now we construct a set. So I construct a set, suppose I write A, and that set contain the element V1, V2, VR, UR plus 1, UR plus 2 up to UM, and WR plus 1, WR plus 2, WP. So we construct the set containing all the linearly independent vectors such that, so let we construct a set this, and if we are able to show that, first thing is that A is Li, linearly independent, and the second one is A spans U plus W, then we can claim, we can say that A is a basis of U plus W and contains, so it contains R plus M minus R plus P minus R. So, that become basically M plus P minus R elements. So, these things will be there. So, now we need to show that A is linearly independent and A spans the whole U plus W. Now, so let us prove first one. We need to show that A is linearly independent. So, this one we need to show. So, from here I will write, I will take the linear combination of the elements this, which implies that suppose I take alpha 1 summation, I take alpha I and Vi I from 1 to R plus summation beta I Ui, I is moving from R plus 1 to M plus summation I from R plus 1 to P alpha beta gamma I Wi. Suppose I take the linear combination for this one. So, I take the linear combination. So, this is the linear combination. So, we need to show that alpha i's, beta i's and gamma i's all are 0. So, that we need to show. Now, from here I can write this as summation I from 1 to R alpha I Vi plus I from R plus 1 to M beta I Ui can be written as minus sign with gamma I Wi R plus 1 to P, and let this is equal to V, some V I just take. It means I am taking this as a vector V. Now, from here I can say that V is can be written as a linear combination of vectors in U, because Vi and Ui's are the basis for the subspace U, and taking this linear combination I am getting the value V. So, which implies that V belongs to U, the spanning of U basically it is U. Also, V is minus summation R plus 1 to P gamma I Wi, which implies that V is also can be written as a linear combination of Wi's. So, it means that V also belongs to W. Now, from here if V belongs to W, then which implies that V also belongs to U intersection W. So, if belongs to U intersection W implies that V can be written as some linear combination delta I Vi I from 1 to r, because these are the bases, Vi are the bases for u intersection w. So, now from here I can write that, so V is already this one. So, from here I can write that minus summation gamma I Wi I from r plus 1 to p is equal to summation I from 1 to r delta I Vi and from here I can write that summation delta I Vi I from 1 to r plus summation gamma I Wi I is moving from r plus 1 to p equal to 0. So, now it is a Vi and Wi, already we know that they are the basis for w. So, from here it is very easy to check that it means that delta I and Wi all are 0 for all I, because the set V1, V2, Vr and W r plus 1 up to Wp is a basis, for W. So, from here all the delta i's and Wi becoming 0. So, if delta I and Wi becoming 0, then from here, so I just can give the name of this equation. So, let us write it's 1. Then from equation 1 we get, so now gamma I became 0, oh sorry, this not W, it is gamma. So, gamma is became 0. So, this gamma became 0. So, from here I will get that summation I from 1 to r alpha I Vi plus summation I from r plus 1 to m beta I and ui, that became 0. Now, this is already, if we put equal to 0, which implies that all alpha i's and beta i's are 0 for all I, because this set V1, V2 up to Vr, u r plus 1 up to um is linearly independent, that we already know because it is a basis. So, from here we can say that, which implies that the set A is linearly independent. So, this is, we are able to show that A is linearly independent. Now, we need to show that A spans u plus w. So, it is very easy to show. Now, so second one we need to show. So, now we need to show that A spans u plus w. Now, let I take element z belongs to u plus w, which implies I can write z as some element u plus some w, and which again, because if it is in the u, I can write this as a linear combination I from 1 to r some ai's into vi's, because I from r plus 1 to m bi and ui. because this is the basis for this one, plus similarly I can write this one as I from 1 to R A B. So, I can write as C I V I plus summation I from R plus 1 to P some D I and W I, because this element W belongs to W and this U belongs to U. So, U can be written as a linear combination of this one and W can be written a linear combination of this one. So, after writing this one, I can from here I can say that, which implies, because this can be combined. So, I can write that Z becomes equal to, so this summation I can write as I from 1 to R A I plus C I can take common V I plus the remaining B I U I plus the remaining D I W I, and which is, if you see, that is a linear combination of the vectors of A. So, which implies that Z belongs to the span of A. So, from here we can see that Z belongs to the span of A. It means that I started with a Z from U. So, from here I can write that U plus W is contained in span A. Also, because A definitely contain the elements, the vectors, and all vectors are coming from U plus W. So, also I can say that A span is subset of U plus W, because I can take the element A from the span of A, and that can be shown with this, that belongs to U plus A. So, from here I can, using this and this condition, I can say that U plus W is equal to the span of A. So, it means from here I can say that A is a basis for U plus W. Now, if it is a basis of U plus W, then definitely I can check that the dimension of U plus W is, so we have shown this one, that it contains M plus P minus R elements, is M plus P minus R. So, that is equal to dimension of U plus dimension of W minus dimension of U intersection W. So, that is the proof of the given theorem. So, now we will stop here. So, today we have discussed very important theorem, that the dimension of U plus W, that is a subspace of a given vector space V, that is equal to the dimension of U plus dimension of V minus the dimension of their intersection. So, I hope you have enjoyed this one. Thanks for watching. Thanks very much.